All right, chapter 27 concerns fluid electrolyte and acid-base balance. Very important but yet complex area of physiology. This presentation will focus on fluid and electrolyte balance, and then part two we will talk about acid-base balance. All right, these are two headlines in newspapers in the last few years. Woman dies after water drinking contest, right? Water intoxication. What in the world is water intoxication? We hear about intoxication of, due to a lot of other things, different drugs, alcohol, etc. But what about water, right? Water's supposed to be good for you. And indeed, it is good for you. We are roughly 70% water, right? But too much of a good thing can be a bad thing, and that includes water, as we're going to see. So, if too much water is actually bad for you, how can this be? Well, to answer that question, we need to look at what actually occurs inside our bodies when we ingest water, especially when we take in too much water. As we're going to see, a delicate balance must be maintained between cells and surrounding tissues vis-a-vis water volume, electrolyte concentration, and the distribution of water among the various compartments of the body. Now, as we know, we're roughly 70% water, right? So the question is, how is that water distributed? In other words, what are the compartments, if you will, that we can talk about in which water is distributed? And how is it distributed, and how does that distribution in terms of volume change under different circumstances, right? And understanding this will get us far along the road of understanding, why and what happens when too much water is ingested, or indeed too little is excreted. All right, so when we're talking about body fluids, we begin by talking about total body water, right? And that's the sum total volume of all the water in our body, right? We can subdivide that, as I said, into compartments, right? And the two major subdivisions are the intracellular fluid, or ICF, right? And I also have that here, right? And the extracellular fluid, or ECF, right? And that's over here, okay? The majority of body water actually is inside our cells, right? The largest volume of water is inside our cells. And it's the watery component of the cytoplasm, which is called the cytosol, right? So 2/3 of our total body water volume actually resides inside our cells, cells. The other compartment, the ECF, or extracellular fluid compartment, has about 1/3 of our total body water volume, and this compartment can be subdivided into two subcompartments. The larger of the two subcompartments, and depending upon the sex of the individual, body mass, and so on and so forth, the interstitial fluid is about 70% of the ECF, right? So of that 1/3 of total body water that the ECF represents, about 70% of it is interstitial fluid. Now, this is the fluid that is between our body cells, the fluid environment, or fluid medium, if you will, in which our cells and tissues reside and are surrounded by, right? And then the other 30% or so is fluid inside our vasculature, inside our blood vessels, and that's known as the intravascular fraction of the extracellular fluid, right? So we have the intracellular fluid and the extracellular fluid. The intracellular fluid has the largest or larger fraction of total body water. The extracellular fluid compartment can be subdivided into the interstitial compartment and the intravascular compartment. The interstitial compartment has the greater share of the ECF, and the intravascular compartment the remainder. Right now, the intravascular compartment is extremely important. Right, this is the fluid that comprises the plasma of our blood, for instance. Right, and is responsible largely for our blood volume. Right, and our blood volume is an important parameter or variable that determines our blood pressure. So changes in the intravascular fluid can be very, very important, right, in terms of the well-being of the organism, the well-being of the individual, as we're going to see. Now, this diagram just gives you another look at what I mean by intracellular versus extracellular fluid, right? So, on this side of here's our phospholipid bilayer, our plasma membrane, right? On the cytoplasm side is where we find the intracellular fluid, and then the extracellular fluid is all the fluid that's not inside a cell, right? And again, we can subdivide this compartment into interstitial fluid as well as intravascular fluid. Now, an important concept to understand and keep in mind is that the two compartments, the intracellular fluid and the extracellular fluid, are in communication with one another, right? In other words, the fluid in those two compartments freely communicate with one another. And they do so across this structure right here, which is, of course, the plasma membrane, right? As we know, the phospholipid bilayer of the plasma membrane is freely permeable to water, but only selectively permeable to certain other things, right? For instance, ions, being charged particles, are not at all permeable, in terms of passage through the cell membrane. They need specialized channels to make it across, right? And ions serve as the major solutes of the fluid in both of these compartments, intracellular fluid compartment and extracellular fluid compartment, all right? Now, we know from our understanding of osmosis, right, that water will move across a selectively permeable barrier, like the cell membrane, in a way which is dependent upon the differential solute concentration in the fluid across that semi-permeable barrier or membrane, right? So, two key questions we need to answer and understand the answer to them. And that is one, if you drink a hypotonic solution, right, what changes will that cause in the extracellular fluid compartment with respect to the intracellular fluid compartment? In other words, what kind of shift in the distribution of fluid will occur across this semi-permeable barrier if you were to ingest a hypotonic solution? Now, the question is, hypotonic to what, right? Hypotonic to what? Well, when you drink water or any other liquid, right, the first place that ingested fluid will distribute to is the extracellular fluid, right? So when we say drink a hypotonic solution, we mean add a hypotonic solution to the extracellular fluid, meaning it is hypotonic relative to the tonicity of the intracellular fluid. Now remember the concept of tonicity, right? Tonicity refers to solute concentration. Remember that hypo, the prefix hypo means beneath, or we kind of use that interchangeably with less than, right? So drinking a hypotonic solution means you are adding fluid volume or adding a solution to the extracellular compartment here, whose solute concentration is going to be less than the solute concentration of the intracellular fluid compartment across this membrane, right? So here I have the solute concentration across this membrane is relatively equal, right? In other words, the solute concentration inside the cell and the solute concentration outside the cell in the ECF, they are equal, right? So when we have equal solute concentration, we are not hypotonic, nor are we hypertonic, right? These two fluid compartments are what? They are isotonic to one another, right? As I have currently drawn them, all right? However, if we add a dilute solution, right? A dilute solution, meaning a solution that has less solute concentration to the ECF than does the intracellular fluid solute concentration, what I end up doing, all right, as you might imagine, what I end up doing is lowering the solute concentration of the extracellular fluid compartment. So now we can sort of represent that depending on how dilute the solution we're drinking is, right? Perhaps the solute concentration drops down a little bit, right? Drops down, right? So now we are no longer isotonic, right? Now the extracellular fluid compartment is hypotonic relative to the intracellular compartment. And we can equally say that the intracellular fluid, this compartment, is now hypertonic relative to the extracellular fluid compartment. All right, are you following me? Now, question is, when we have a differential solute concentration across this membrane that's freely permeable to water, the first question you need to ask yourself is water going to move? Right? Well, we know that osmosis is simply the diffusion of water. Therefore, that means that water is going to move from a region of higher water concentration to a region of lower water concentration. So, question, which of these compartments, ICF or ECF, now has the higher water concentration? Right? Well, remember that the region that has the higher water concentration is going to have the lower solute concentration, right? Okay, and the region that has the lower water concentration has the higher solute concentration. So as we can see by the way I've drawn this, the ECF now has the lower solute concentration and therefore the higher water concentration, right? So based upon the rules of osmosis, what's going to happen? Well, water volume is going to move from the ECF into the ICF, i.e. inside the cell, right? Until what? Until the solute concentrations across the membrane are equal one another. In other words, until we become isotonic again. Now, the price we pay for this isotonicity, i.e. the same solute concentration across the membrane, is we have different volumes of water across this membrane, right? Different volumes of water across the membrane. We have to have a greater volume of water inside the cell than outside the cell in order to equilibrate the solute concentration, right? So the answer to this first question, therefore, drinking a hypotonic solution causes what change in the ECF with respect to the ICF, right? We end up lowering the solute concentration in the ECF, right, compared to the ICF. And then the further consequence of that is water or fluid volume is going to shift from the ECF to the ICF and will continue to do so until the solute concentrations are equal again or isotonic, right? Okay? Now, same concept applies to our second question here. Drinking a hypertonic solution causes what change in the ECF with respect to the ICF? Well, this is a situation now where we're drinking, we're ingesting, say we have Gatorade that we've added 3 tablespoons of salt to or something, right? We're drinking a solution that has a much higher solute concentration than does either the ECF or the ICF, right? So remember, we start out being equal, right, or relatively equal solute concentration across the cell membrane. But now I'm drinking something or, ingesting a fluid of some sort that's going to add a hypertonic solution to the ECF. And in this case, what we end up with is a higher solute concentration in the ECF than we have in the ICF, right? So now, question to ask is water going to move? And the answer is yes. And why is it going to move and how is it going to move? Well, it's going to move according to the rules of osmosis. It's going to move from the region of greater water concentration to the region of lower water concentration, i.e. it's going to move from the region which has the lower solute concentration to the compartment with the higher solute concentration, right? So water is going to move out of the cell, right? And it will continue to do so until the solute concentration is once again equal or isotonic across this membrane. The price we paid for this isotonicity or this reaching equilibrium is that the volume of the ECF compartment has increased and the volume of the ICF has decreased. right? So we have a net fluid shift because of changes in that solute concentration, right? So this is the way we need to look at fluid balance between these two compartments. And indeed, what often changes that balance is not, doesn't necessarily have to be an addition or subtraction of fluid, but it can also be an addition or subtraction of solute, right? So changes in either fluid volume or solute concentration can cause fluid shifts across these two compartments. Now we're talking about solutes, right? Solutes whose concentration influences volume shifts across these compartments. Really what we're talking about are ions, right? Because remember, one of the important principles of osmosis is that we have a membrane that's permeable to water but impermeable to solutes, right? And the cell membrane, as we know, is impermeable to charged or polar molecules, right? So ions are really the solutes that we're talking about that most influence fluid shifts across these compartments, all right? And this is by way of review, some significant ions. There are others, but these are sort of the top, the top list in terms of importance. Sodium, potassium, calcium, chloride, magnesium, phosphate, bicarbonate, the hydrogen ion, hydroxide, and so on and so forth. In terms of fluid shifts, in terms of osmotic balance, if you will, across the membrane, these two ions, the sodium ion and the potassium ion, are very, very important. And that's simply because their concentration, right, in both the ICF and ECF, the potassium, really we can think of as an intracellular ion, right? We find potassium in highest concentration inside the cell. And the sodium ion is really an extracellular ion, right? There is sodium inside the cell, just like there's potassium outside the cell. But its concentration inside the cell for potassium ion is much, much higher, and the concentration of sodium ions outside the cell is much, much higher than inside, right? And relative to most of these other ions listed, the concentration of these two far outweighs the others. Now, calcium is a close second, right? Calcium is chiefly an extracellular ion in most circumstances, right? But in terms of fluid shifts, in terms of solute influence on fluid volume shifts across these compartments, ECF and ICF, we're really talking about sodium and potassium, such that we can sort of kind of ignore the rest of them. And that does not mean that these are not critically important in their own way for many, many things. But in terms of volume shifts, right, fluid balance, sodium and potassium are the major players. Now, as such, right, the electrolyte concentration in the extracellular fluid compartment is what largely affects fluid shifts across the two compartments, ECF versus ICF, and therefore affects the fluid volumes in both of those compartments, right? Now, what we mean by electrolyte, there's a formal chemical definition, but the definition that I really want you to remember is an electrolyte is a charged particle in water, right? So really what we're talking about is ions in water, right? Its formal definition is, any particle that can conduct an electrical current through water, right? But ions are charged particles, so they can do that. The most common electrolytes, derive from sodium chloride, right? Sodium chloride and potassium chloride, right? This is table salt, sodium chloride, right? And what happens when and sodium chloride, the bond between the sodium and the chlorine atom here is simply based upon their ionic charge, right? The positive charge of the sodium is attracted to the negative charge of the chlorine, and they come together and form an ionic bond and form the ionic compound sodium chloride. Well, when you drop sodium chloride in water, what happens is, right, the water, H2O, the water interposes itself between these two ions, sodium and chloride, if you will, and breaks them apart so that they now exist freely in the water, in the solution, right? And now they are electrolytes. They are charged particles floating around in water. And I said in the previous slide that the major solute in the extracellular fluid in terms of, those solutes that affect fluid balance and fluid shifts across the two compartments is sodium, right? Right. So the chief ECF electrolyte, therefore, is sodium. Okay, so really it's sodium concentration in the ECF that's going to affect fluid shifts and overall fluid volume between the ECF and the ICF, right? And the adage, where sodium goes, water soon follows, right? i.e., okay, if we're in the intravascular compartment, which is one of the subcompartments of the ECF, right? In blood, what we're talking about is the intravascular fraction, right? We're talking about the intravascular compartment, or IVF, of the ECF, right? Okay, so we're still in the ECF. So sodium, whether we're in the intravascular fluid or in the interstitial fluid, they're both part of the ECF. And since sodium is the chief electrolyte in the ECF, sodium concentration in the blood is also going to affect the overall blood volume, right? If the concentration of sodium in blood increases, the volume of blood is going to increase, right? And the opposite is also true. If blood sodium concentration decreases, blood volume soon decreases, right? Because sodium ion is the chief osmotic solute in the ECF, right? And when its concentration goes up, the solute concentration across the two compartments changes. And whenever the solute concentration across the two compartments, ECF versus ICF, is different, we are going to have a shift or movement of water across those two compartments to equalize that solute concentration, right? So that they are once again isotonic. Now, we know, of course, how important water is. Water is important for many, many things. We're 70% water, right? And the, ECF compartment, the extracellular fluid compartment, which comprises both interstitial fluid and intravascular fluid, 99% of the ECF is water, right? 99% consists of water. And when, water volume is low, lots of bad things happen, right? Proteins denature, in other words, proteins unwind and become unfunctional, dysfunctional. And since enzymes, as we know, are proteins, they can cease to function. And if enzymes cease functioning, most biochemical reactions in the cell and outside the cell also stop functioning, right? And the end result of this is cells begin to die, right? And as more cells die, the greater the organism dies, right? Until death itself is reached, right? So it's, these issues of water volume and fluid shifts are very, very important for the health of not only the individual cell, but for the entire organism. As such, it is critical to keep in balance, right? To maintain a homeostatic balance between the overall volume of fluid across these two compartments, right? The volume of fluid in the ECF and the volume of fluid in the ICF, right? And also, and contributing to that, is going to be maintaining a balance of solute concentration, right? If we're going to keep, volume constant in terms of ECF versus ICF, we know we have to keep the solute concentration balanced or isotonic between the two compartments, because if we don't, we're going to have a shift in volume between those two compartments, right? The third parameter that we must keep in balance for different reasons, of course, is pH, right? When the pH changes, all sorts of nasty things can happen, right? But we're going to put our discussion of pH changes off until the second presentation in this chapter. Right, now, the body does have a mechanism, right, to monitor the state of affairs, right, especially vis-a-vis solutes and fluid volume. However, there are a couple of things to keep in mind, right? One, yes, there are mechanisms that monitor and are able to adjust the composition of body fluids, but they do so by monitoring changes in the extracellular fluid, right? The body does not have receptors or monitors, if you will, for changes that are occurring in the ICF, right? So it's changes in the ECF, right, that are detected and that put into play compensatory mechanisms to help maintain body fluid balance, right? The second principle is that there are no receptors or monitors, if you will, that directly monitor the balance of fluids and solutes, fluids and electrolytes. Rather, what we have are receptors throughout the body in different places in the body that monitor overall plasma volume and they monitor solute concentration, right? They do not monitor the balance, right, between the fluid compartments, right? They monitor volume change and changes in solute concentration, but they do not directly monitor whether or not the balance of fluid and solute concentration is maintained across the two compartments. Third principle, and I think we're all familiar with this by now, hopefully, is that cells are not able to move water molecules against a water concentration gradient. In other words, they don't actively pump water out of themselves, right? Water moves solely according to osmotic gradients, right? In other words, water concentration gradients. Because as we've said, osmosis is simply the diffusion of water, right? And like the diffusion of anything, right? Water will move from a region of higher water concentration to lower water concentration, right? And how do we know where water is higher and lower concentrated? Well, we know that by reference to the solute concentration, right, in the two compartments, right? And as we know, the chief extracellular fluid solute is sodium, right? Okay? And whenever sodium or other solutes are moved across the cell membrane or a tissue, right, water is going to follow in order to equilibrate the solute concentration across the cell membrane, right, between the ECF and the ICF. And a fourth principle here is that, the body's overall content of water or solutes can rise or will rise if you take in more than you excrete. So if dietary gains exceed losses to the environment, right? And also, the body's content of water and solutes will fall if losses exceed gains, right? Now, as we said, the body has receptors, if you will, or monitoring mechanisms to monitor both solute concentration and overall water volume, but no mechanism to directly monitor the balance between solute concentration and water volume across the ECF and the ICF, right? We have solute concentration monitors or receptors, and we have, volume monitors or receptors, right? In terms of solute concentration monitoring, if you will, really what we're talking about is monitoring the osmotic concentration of the body fluids, right? In other words, the concentration of solutes that are going to affect osmosis, right? And we call receptors that monitor that solute concentration, we call them osmoreceptors, right? Osmoreceptors. Now, the hypothalamus in your brain has special cells that are osmoreceptors, and their role is to monitor the solute concentration of the extracellular fluid. Because remember, the monitoring that goes on is solely of the ECF. There is no set of receptors or organ or capacity for the body to monitor these changes inside the cell. So we're talking about changes in the ECF. So osmoreceptors in the hypothalamus monitor the solute concentration of the extracellular fluid fraction, right? And the hypothalamus, via the pituitary gland, the posterior pituitary gland, is able to release antidiuretic hormone, right? For instance, if the solute concentration in the ECF rises, what do we need to do to bring it back down, right? Well, we could do two things. We could excrete more solute, i.e. in the urine and the kidneys, or we could retain more water, right? We could retain more water, right? So in terms of ADH, right, we're already old friends with ADH, right? In terms of ADH, this is the hypothalamus's attempt to lower a solute concentration or an osmotic concentration of the ECF that is too high, and it's going to do so by retaining fluid, right, by inhibiting excretion of water in the kidneys, right? We know that antidiuretic hormone is going to act on the collecting duct and distal tubule of the nephron to allow water to be reabsorbed, right? And the reabsorption of that water is going to dilute the ECF, if you will, to bring the osmotic, i.e. solute concentration, back down to normal, if you will, or homeostatically appropriate. And as we said, right, water reabsorption, specifically at the collecting duct and distal tubule, right, so that the urine is concentrated and water is reabsorbed, right? Also, ADH will stimulate the thirst drive, right, so that you bring in more water, right? And that also acts to dilute the ECF fraction to bring its solute concentration back down to normal. All right, so the hypothalamus and ADH, right, we're talking about changes in the solute concentration, the osmotic concentration of the ECF. How about changes in volume, right? Changes in volume. Well, remember the juxtaglomerular apparatus at the nephron, right? The juxtaglomerular apparatus was really a pressure sensor, right? But only indirectly. In other words, as renal blood flow, right? Blood flow entered the kidneys, makes its way to the afferent arteriole, which brings blood into the nephron. The cells of the juxtaglomerular apparatus, remember the JGA, right? And if you don't remember what that is, I urge you to pause this and go back to chapter 26 and review this discussion about the JGA, renin, and aldosterone, and so on and so forth. But the cells that make up the juxtaglomerular apparatus monitor blood flow through the afferent arteriole as it enters the glomerulus, right? And really what they are stretch receptors, right? And what they're monitoring, though, is volume of blood flow. In other words, as if volume of the blood flowing through the afferent arteriole decreases, then the degree of stretch on these cells, in other words, the stretch on them is going to decrease, right? And the JGA interprets that reduction in stretch as a reduction in fluid volume entering the glomerulus, right? So the JGA says, whoa, wait a minute, right? Fluid volume is too low. And remember what we're talking about when we're talking about blood flowing in a blood vessel. We're talking about the intravascular portion of the ECF, right? So we're still in the extracellular fluid compartment. In other words, we're still monitoring changes in the ECF, right? Well, what does the JGA do when it recognizes a decrease in volume of blood flow in the afferent arteriole? Well, remember, it releases renin, right? Renin finds angiotensinogen that's made by the liver and released into the blood, right? And when renin reaches angiotensinogen, it changes angiotensinogen into angiotensin 1. And angiotensin 1 makes its way to the pulmonary capillaries, which have on their surfaces the enzyme, what? Do you remember? Right? We have angiotensin converting enzyme, which converts angiotensin 1 to its most active form, angiotensin 2, right? And we know that angiotensin 2 travels to the adrenal glands, right? To the adrenals, and the adrenal glands release aldosterone, right? And what does aldosterone do? Aldosterone increases the rate of sodium ion reabsorption in the collecting duct and distal tubule. And when we reabsorb more sodium into the extracellular fluid compartment, what are we doing? We are raising the solute concentration in the extracellular fluid compartment. Water is going to move, water is going to follow, right, via osmosis. So this stimulates water reabsorption back into the intravascular subcompartment of the extracellular fluid compartment, right? And in doing so, we retain more water, right? And we increase our fluid volume of the extracellular compartment, right? An indirect function of aldosterone is also makes you crave salt, right? It makes the salt receptors on your tongue much, much more sensitive, so you actually crave salty foods. All right, so the juxtaglomerular apparatus and renin and angiotensin and aldosterone, right? Those that was a response to a reduction in fluid volume, right? This is how the body compensates for what it perceives as a loss of fluid volume. But what happens when fluid volume is too high, right? Well, this is where the natriuretic peptides, right? Atrial natriuretic peptide ANP and brain natriuretic peptide BNP, right? Their names have nothing to do with where they come from or how they act, right? The names have to do with where they were first isolated in animal models, right? But both these natriuretic peptides ANP and BNP act to lower, right? In other words, they are released and result in the lowering of fluid volume by increasing the excretion of water, mainly at the kidneys, right? They also act to reduce thirst. They block the hypothalamus release of ADH. They block the release of aldosterone from the adrenal glands, the adrenal cortex, and they act to therefore promote water loss in the urine, right? And when we lose water in the urine, we are losing total extracellular fluid volume, and lowering blood volume tends to lower blood pressure, right? So the natriuretic peptides are released in response to too much fluid volume in the extracellular fluid compartment. And remember that renin, angiotensin, and aldosterone were released by the juxtaglomerular apparatus of the nephron when fluid volume was perceived or sensed to be too low. Now, it's important to remember that the two subcompartments of the ECF, right? So remember, here is our extracellular fluid compartment, and the two subcompartments are the interstitial fluid, right, and then the intravascular fluid, right? So the intravascular fluid is the fraction of the ECF that's inside blood vessels, and the interstitial fluid is everything else, right? All body fluid that is not inside cells and not inside blood vessels, right? That's the interstitial fluid, right? Well, these two subcompartments of the ICF are also in direct communication with one another, in that there's continuous filtration, as the slide says here, continuous exchange of fluid from the IVF and the to the EV from the IVF to the IF, if you will, and vice versa. And this is at the level of the capillaries, the smallest arterial blood vessels. And remember that capillaries are the exchange vessels, right? They exchange oxygen and carbon dioxide and nutrients, right, with the cells that surround them, the tissues through which they course, if you will, right? But they also freely exchange water, right? Freely exchange fluid between capillary blood and interstitial fluid, all right? And what governs that exchange are certain forces that we call the Starling forces that operate the capillary. Now, these are things that we have talked about earlier in the term, but let's just go over them again because it will allow us to understand how it is that these fluid volume shifts can occur in and out of blood vessels, if you will, that affect blood volume and therefore blood pressure, right? So here we are, in a capillary. We have blood flowing into the capillary from this end, and this blood came from arterioles, which came from arteries, which came from the aorta, which came from the left ventricle of the heart, say. Right? So the blood entering this capillary is under a certain pressure, and when it enters that capillary, the pressure of that blood is going to press up against, right, against the wall of the capillary, right? And we call the pressure of the blood entering the capillary the blood hydrostatic pressure, right, or BHP, right? Blood hydrostatic pressure over here, all right? And as I said, this pressure is pressing water or fluid molecules against the walls of this capillary. And since water is freely permeable across a wall of a capillary, because a wall of a capillary basically is single celled. It's a simple squamous epithelial cells comprise the wall of a capillary, right? So this pressure is driving water basically across the capillary wall and out here into the interstitium, right? Okay. Now, the interstitium, right, also has fluid in it, right? That's the interstitial fluid. The interstitial fluid also has a certain pressure, if you will, right? And that is called the interstitial hydrostatic pressure, right? And that's this right here, the interstitial hydrostatic pressure listed over here on the right, all right? Now this pressure, right, this pressure, and we'll use a different color for that, right? The interstitial hydrostatic pressure is a pressure that's pushing against the outer wall of the capillary, and it wants to push fluid back into the capillary. All right? Now, when blood enters the capillary here on this end, right, the blood hydrostatic pressure is higher than the interstitial fluid hydrostatic pressure, right? So water is going to leave the capillary as the blood courses through the capillary in this direction, right? But as it does so, and more fluid leaves the capillary, the blood hydrostatic pressure is going to drop, right? It's going to decrease as that blood courses through the capillary because more and more of it is leaving the capillary at each stage of its journey, right? But where is it leaving to? It's leaving to the interstitium. And because that fluid is entering the interstitial fluid fraction, its pressure, its hydrostatic pressure, is increasing, right? So as the hydrostatic pressure of the fluid inside the capillary is decreasing as it courses through, the interstitial fluid pressure is increasing, right? So, in other words, fluid entering the capillary tends to leave the capillary for the interstitial fluid, right? But as we course along here and pressure builds out here in the interstitial fluid, that opposes, right, any more fluid loss from the capillaries, and indeed begins to force fluid back into the capillary, right? So what was lost up here can begin to return here, all right? Now, there are a couple of other forces, if you will, that we need to take into account, and that's this right here, which stands for the blood oncotic pressure. But I would like you to think of the word oncotic. There's that word right here, oncotic, right? I would like you to think of oncotic basically equals osmotic, right? Okay, so in other words, what we're talking about is the influence of solutes, right? In other words, what's left in this capillary that cannot cross this capillary wall? Well, we know that water can freely cross it. We just talked about water crossing it back up here, didn't we? But the one thing that cannot freely cross cell membranes are certain solutes, like proteins, right? Proteins are large molecules, or they tend to be, and they also have a net negative charge. And because of their size and because of their negative charge, they cannot freely cross the cell membrane, and therefore they cannot freely cross a capillary wall. So even though water is exchanging with, between the intravascular fluid in here and the interstitial fluid out here, the proteins and other solutes, but the proteins in the blood are not. They are staying put right here in the intravascular fluid. As such, right, as fluid or as water leaves the capillary for the interstitial fluid, the solute concentration in the interstitial fluid begins to drop because the fluid leaving, the water fraction of the blood in the capillary leaving the capillary dilutes the solute concentration of the interstitial fluid, which we call the interstitial oncotic pressure, by the way. We can refer to the influence of the solutes in the interstitial fluid out here. We can call that the interstitial oncotic pressure, right? So as the solutes out here become dilute, right, the solutes remaining in here, their concentration rises because water has left back up here. So now we have a solute gradient, don't we? We have a solute gradient in which solute concentration in the capillary is much higher than solute concentration out here in the interstitial fluid. So that also acts to bring water, right, to bring water back in to the capillary at this end, right? So the shift in hydrostatic pressure, i.e. the blood hydrostatic pressure when we first enter the capillary is higher inside the capillary than it is outside. So that forces water out of the capillary. But as more water is forced out, there's less water remaining in the capillary, and so the pressure of that fluid in the capillary begins to drop as we course along the capillary, but builds out here as we go along, right? So the hydrostatic pressures vis-a-vis the interstitial fluid and the intravascular fluid, they reverse, such that as we course along, water will tend to come back into the capillary. Also, we have the differential solute concentrations, right? As water leaves the capillary, that water is going to dilute the solute concentration out here and concentrate the solute concentration in here, right? Which also creates an osmotic gradient that will draw water back in, right? Such that we don't, when we lose blood, if you will, from the capillary to the interstitium, we reclaim most all of it by the time we get to the other end of the capillary. Now, in truth, we don't reclaim all of it. There's a small fraction that actually is not reclaimed that remains out here in the interstitium. But this is where the lymphatic system comes into play. The lymphatic system drains the excess fluid and returns it to the intravascular compartment at the left subclavian vein, right? It's where the lymphatic system empties into the blood system at the left subclavian vein, all right? Now, you can just imagine, right, that we could have serious shifts in the way this works if we change any of these forces that we've talked about, any of these Starling forces, right? In other words, if the pressure of the blood entering this capillary is much, much higher than normal, right? Much, much higher than normal. That is to say, the pressure pushing fluid against the walls of the capillary and driving it out of the capillary. If this blood is under way too high pressure, too much water is going to leave at this end. We're going to lose too much water out here, such that our other reclamation mechanisms, like our oncotic pressure differential, in other words, the changes in the solute concentration on the other end, are overwhelmed. Right? Too much water left here because it is under too high a pressure here, such that we cannot reclaim enough by the time we reach the other end of the capillary. In other words, too much water remains out here in the interstitium. And it even overwhelms the lymphatic system's ability to drain it and return it to the circulation. So what have we done? We have increased the volume of the interstitial fluid compartment relative to the intravascular compartment, right? And that is called edema, right? We have a shift of volume from the intravascular compartment to the interstitial compartment, right? Now, that can be quite serious. Number one, that excess fluid volume out here can put pressure on delicate structures and cells and cause dysfunction or even death. But the other thing is the loss of fluid from the intravascular compartment here lowers the blood pressure, right? Lowers the blood pressure, and blood pressure is what drives blood flow. And so, as you can imagine, that can be a very, very serious thing to happen, right? On the other side of it, right, we could change the interplay of these two forces here, right? We could change the interplay of the solute concentrations across the capillary wall. In other words, we said that the proteins in blood are responsible for much of the solute concentration that exerts an osmotic effect on drawing water back in the capillary. Right, well, what if the concentration of protein in the blood drops for some reason, right? Most of the proteins in the blood are made by the liver, right? Well, let's say that the liver is damaged or diseased and is not making sufficient protein. If we don't have sufficient protein in the blood, the solute concentration of that protein in the blood is going to drop, right? And therefore, right, if we don't have enough solute concentration in here, we don't have the osmotic force, if you will, to draw fluid back into the capillary that left on this end, right? This can also happen at the level of the nephron in the kidney. Remember that proteins are not supposed to be filtered at the glomerulus. They're supposed to remain in the blood. Well, what happens if the glomerular filtration membrane is damaged and proteins are allowed to be filtered, and they end up going out in the urine because, the tubular system is not used to seeing protein. It's not supposed to be filtered at all. So if protein ends up in the tubular fluid, the tubules of the nephron can't reabsorb it. So whatever ends up in the tubular system is gonna go out in the urine, right? So if we're wasting protein in our urine, our protein concentration in our blood is going to drop, and therefore we lose that osmotic solute that's going to exert osmotic force, if you will, to help us reclaim water from the interstitial fluid that has been lost up here at this end of the capillary. Either way, we're going to end up with an accumulation of abnormal volume outside here in the interstitial fluid compartment at the expense of volume here inside the capillary or inside the intravascular fluid compartment, right? And so we get swelling or edema in our interstitium, and we get a loss of blood pressure due to a loss of plasma volume from the capillary. Now, it should make sense to you that in order, for fluid balance to be more easily maintained, right, fluid gains and fluid losses have to be balanced vis-a-vis one another, right? Whenever we gain more than we lose, fluid volume is going to increase, and whenever we lose more than we gain, fluid volume is going to decrease, right? So to understand that a little better, we need to understand how it is that fluid volume is gained and lost in our bodies, right? Well, we actually metabolically generate water, right? We metabolically generate water in the intracellular fluid. We do that inside the cell. Remember our equation for aerobic respiration, for instance, right? We said that, glucose, right, in the presence of oxygen yields carbon dioxide and water, right? In the process, we make ATP, right? That's really what we focused on when we talked about this equation. But look at this, right? We generate water through aerobic metabolism, through the breakdown of carbohydrates, right? So that's what this diagram is talking about, the metabolic generation of water. And other processes too, but we're very familiar with this one, all right? And of course, because the cell membrane is freely permeable to water, the ICF communicates with the ECF, all right? So we generate water this way, right? We also absorb water every day that we ingest, and we do so across the alimentary tract, right, across our digestive epithelium. And as we said earlier, water that we ingest or fluid that we ingest enters the extracellular fluid compartment, all right, at least first, right? That's where it goes, all right? So that's how we, gain fluid, right? We gain it metabolically and we gain it by ingesting it in our diet, all right? So how do we lose fluid? Well, we lose a little over a liter a day in our urine, right? Now, as we know, the nephron, the kidneys can vary this by the mechanisms that we've discussed, but on average, we lose a little over a liter or so every day, right? We also lose fluid every time we exhale, right? Because there's water in our airway, there's water in our lungs, and every time we exhale not only air and carbon dioxide and such, we also exhale water vapor, right? We also sweat, right? We sweat. It varies depending upon our activity level and external conditions, but we sweat, right? And we call sweat sensible perspiration because we're aware of it. We can look down and we can see it, we can feel it, right? But we also perspire insensibly, right? In other words, our skin, our integument is not completely water resistant or water impermeable, right? It does help to, keep body water inside and keep external water outside to a certain extent, but water vapor actually can make it through the integumentary barrier. So 24 hours a day, we are losing water vapor, if you will, to our environment, even though we can't see it, we can't necessarily feel it. Because of that, we call that insensible perspiration, right? And we lose about a liter of our body water a day every 24 hours that way, right? So these are our gains and these are our losses, right? We also lose water, in fecal matter, right? So urine and fecal excretion, right? So whenever these gains and losses do not balance each other out, right? Whenever we, gain more than we lose, total fluid volume, mainly in the ECF, is going to increase. And whenever we lose more than we generate or gain, fluid volume, mainly reflected in ECF volume, is going to decrease. Now, as we said, sodium and potassium are the major solutes, the major ionic solutes of the extracellular fluid and intracellular fluid compartments, respectively, right? In the extracellular fluid compartment, sodium ion is the major osmotic solute that we need to talk about. Thus, changes in that solute concentration can result in fluid shifts between the two compartments, right? So changes in sodium ion concentration in the ECF can be clinically very, very important and very, very relevant, right? And this slide talks about two clinical conditions that result from changes in the sodium ion and therefore osmotic concentration of the ECF relative to the ICF, right? So hyponatremia, right? Hypo means beneath or lower. Natremia refers to sodium, right? So this is when the sodium concentration in the extracellular fluid drops below homeostatically accepted levels, which is roughly about 130 milliequivalents per liter of fluid. All right, don't need to worry about these units, but that's generally, right? It's usually when it hits about 135 we start to have problems, but below 130 we're in the danger zone, right? And this usually happens, right? Usually, I say, happens not because we, lose sodium ion, right? And now remember, there are two ways that we could lower the sodium ion concentration. We could lose sodium or we could gain water, right? Either of those is going to reduce the sodium ion concentration of the extracellular fluid. Most commonly, this occurs when the water content in the ECF rises such that the sodium concentration drops, right? Also, we can have hypernatremia, a little less common, right? But hypernatremia is a decrease in the sodium ion concentration in the ECF, right? And just like with hyponatremia, we can do that two ways. right? We can increase sodium ion concentration or increase sodium ion content, or we can, decrease the water content. Either of those will end up raising the sodium concentration in the extracellular fluid. All right. Usually, though, the problem is too little water, not too much sodium, right? So it's usually too little water. In other words, dehydration that can result in too high a sodium ion concentration. Now, hyponatremia, as we said, it's a reduction in the sodium ion concentration, the major solute in the ECF, and that's usually a result of overhydration, i.e., water excess. Either you ingest way too much water too quickly, or you can, infuse, say via IV fluids, a hypotonic solution into the extracellular fluid compartment, right? And remember, when we're talking about IVs, we're talking about, intravascular fluid. And then the fluid in blood vessels, veins, are part of the extracellular fluid fraction, right? So if we infuse a hypotonic solution or we ingest too much plain water, we are going to lower the sodium ion concentration in the ECF. Right? If we do so very quickly, we dilute the ECF faster than the kidneys can compensate to eliminate that excess water. Right? More rare are certain endocrine disorders, either disorders in which too much antidiuretic hormone is released, either by the hypothalamus or actually some cancerous tumors, believe it or not, can actually secrete an ADH-like molecule that can cause water reabsorption in the kidneys, right? The sum total of these effects, or together or individually, is water intoxication. Water intoxication, right? We dilute the sodium concentration in the ECF, and as a result, we get fluid shifts between the ECF and the ICF, right? Imagine, if you will, we draw our cell membrane again, right? Here's our cell membrane, and let's say this is a cell in the brain. This is a brain cell, right? This is a brain cell, okay? And let us say that we have diluted the solute concentration out here in the ECF vis-a-vis the solute concentration in the ICF inside of a brain cell, right? So we have a different solute concentration across the cell membrane. The extracellular fluid compartment here is now what? It's now hypotonic relative to the intracellular fluid compartment. So first question, is water going to move? Well, yes, it is going to move because we have a differential solute concentration across the cell membrane. Next question, where is it going to move? In what direction? Right? Well, water is going to move, right, from high water concentration, which is low solute, to lower water concentration, which is higher solute. In other words, water is going to move into the brain cell, right? Now, when water does that, the brain cells swell. Now, when brain cells swell, what are they swelling against? They're swelling against the bony vault of the skull, which ain't going to give, right? That's not going to stretch to accommodate, the swollen brain, right? So what happens is the brain eventually presses up against that hard, bony vault of the skull and strangles itself, right? That pressure will cut off blood flow, and especially in smaller blood vessels, as the blood courses through the brain, blood flow will get constricted and cut off, and the brain will die, right? As this process unfolds, and it usually unfolds gradually, but as it unfolds, right, people have hallucinations, seizures, confusion, they behave like they're drunk until they lose consciousness and go into a coma, right? And the way to treat this, as you might imagine, is to both eliminate fluid and very gradually infuse a hypertonic solution to try and normalize the solute concentration between these two compartments, right? ECF, and ICF. Now, hypernatremia, again, is the sodium ion concentration has increased, and that's usually the result of not of an increase in sodium ion content, but of a decrease in water volume, right? Water content. And this is dehydration, right? Dehydration, when water losses outpace water gains, right? So what happens is, and remember when we're talking about plasma here, right? Plasma is the fluid fraction of the blood, right? And that's part of the intravascular compartment of the extracellular fluid, right? We're talking about the osmotic concentration of the plasma increasing, right? But the real problem here is going to be this, right? A fall in plasma volume because there's too little fluid volume, right? Because of dehydration to maintain blood volume and therefore blood pressure, right? So the key thing to worry about here is going to be circulatory shock. In other words, a drop in blood flow because we have a drop in blood pressure, because we have a drop in blood volume due to the dehydration, right? Now, to compensate for this, what's going to happen is, as we said, we're going to have an increase in sodium ion concentration and just generally solute concentration in the plasma portion of the blood, right? So that the solute concentration of the plasma, i.e. the osmotic concentration of plasma, rises relative to the interstitial fluid surrounding, right, that blood vessel, right? So what we're going to end up having is a fluid shift, right, to try and compensate for this from the interstitial fluid into the blood vessels as a way to compensate for this. As a result of that fluid shift, the interstitial fluid volume, right, so this would be the intravascular portion, this is the IVF of the ECF here, and this is the interstitial fluid portion of the ECF out here, right? So water is going to move because of the solute differential from the interstitial fluid compartment into, right, the intravascular compartment of the ECF, right? So as a result, we're going to get dryness and wrinkling of the skin, right, because all that interstitial fluid has flowed into the blood vessels, if you will, right? And we're also going to get severe thirst because osmoreceptors in the hypothalamus that monitor solute concentration in the blood, as we said earlier a few slides ago, are going to trigger your thirst drive, right? And also trigger a release in ADH, right? Trigger release in ADH as well as aldosterone to try and reabsorb more water in the nephron, right? But in the immediate term, what we're really worried about is this fall in plasma volume and blood pressure that can lead to circulatory shock, right? So what we need to do is try and buttress the fluid inside our blood vessels, right? And we do that by administering hypotonic, right, or infusing hypotonic fluids into our blood vessels, right? And if we do that, right, in other words, we add a dilute solution to the intravascular fluid, and what that does is it dilutes the solute concentration, right? It dilutes the solute concentration, right, here, okay? And we equilibrate the solute concentration between these two compartments, right? So we don't get any net fluid shift from here to here or here to there, and so that whatever that we put into this blood vessel will stay there, right? In other words, we are going to increase blood volume by adding an intravenous solution, right, to this blood vessel, but we want to make sure that we normalize the solute concentration between both sides, right, between the interstitial fluid out here and the intravascular fluid in here, such that whatever fluid we actually put in this blood vessel is going to stay in the blood vessel, right? Remember, before we infuse this fluid, the solute concentration inside this blood vessel was greater than the solute concentration outside it, right? So by giving a hypotonic solution, what we have done is we have decreased the solute concentration in that blood vessel, right? We've decreased it so that it's now normalized or isotonic with the solute concentration in the interstitial fluid outside the blood vessel, such that the fluid that we are giving will stay in the blood vessel, right, and won't leave it, right, and therefore buttress blood volume and therefore blood pressure. And blood pressure will go up and we can prevent circulatory shock. Now, certain things that commonly, can cause extreme water volume loss from the body, excessive perspiration, right? Excessive perspiration, and again, this is a situation in which we are losing more than we're gaining, right? So this is an imbalance in that gain-loss ratio, right? So excessive perspiration from, say, exercising in hot weather, also very, very high fever, right? Severe illness. These things can also cause excessive perspiration, but it's commonly exercising in very hot weather and not, ingesting enough water to compensate for it, right? And that's bullet point number 2 here, right? So inadequate water consumption, excessive perspiration, repeated vomiting, right? Repeated vomiting, you can lose a ton of fluid that way. Diarrhea, right? Diarrhea, increased excretion, we can lose fluid, right? And when we lose fluid volume in these ways, we're losing more water than we are solutes, right? In other words, we're losing water at a much greater rate than we're using solutes. So what ends up happening is we lose fluid volume, and we also increasingly concentrate, right, the solute concentration in the extracellular fluid. Now, how about when we actually gain water, right? Well, drinking pure water, right, will increase our water volume. If we give hypotonic solutions, that's also going to, and again, we're talking mainly about the extracellular fluid fraction, right? If we infuse a hypotonic solution, that's going to end up increasing the volume, fluid volume of the intravascular compartment of the ECF, right? What happens is we get reduced solute concentration in our blood plasma, right? This depresses the secretion of ADH by the hypothalamus, because remember, the hypothalamus secretes ADH when the solute concentration of our blood rises, right? When it falls, ADH secretion is going to be decreased, and thus we have less water reabsorption in the nephron, and thus water loss in the urine is going to increase, right? Plus, we have a decrease in our thirst drive, right? So fluid intake is discouraged, right? Because ADH both promotes water reabsorption in the nephron and also increases your thirst drive. So, most commonly, sodium is the culprit when we're talking about changes in the solute concentration, and it's in the extracellular fluid. It's usually problems with sodium because mainly changes in the solute concentration occur in the ECF, because the ECF is where water is most directly lost, either by perspiration or by excretion in the urine or their feces. And it's also where water goes when it's gained, right? When we ingest water, for instance, it goes into the ECF, right? So changes in water intake and water excretion are usually reflected in the ECF, right? And remember, sodium ion is the chief osmotic solute in the ECF. So any change in the water, content of the ECF is going to affect sodium concentration, right? So usually electrolyte or solute imbalances involve sodium ions in the ECF. But remember, there's potassium, right? And potassium is our chief intracellular fluid solute when it comes to osmotic solutes, that is, that affect fluid movement across the cell membrane, right? So potassium is there and is chiefly inside our cells. Now there's also potassium outside our cells, but its concentration intracellularly is much higher than its extracellular concentration, right? Because of this, problems with potassium concentration, right? In other words, solute concentration vis-a-vis the inside of the cell and the outside of the cell are much less common. However, they are significantly more dangerous to the individual clinically, if you will, than are those related to sodium balance. Now down here I ask why, right? And what I want you to do is to try and think about this for a bit, and we will actually discuss the details of why in lecture together. All right, I will address this in person with you, but I want you to think about this one on your own. I'll give you a hint. One of the reasons it's significantly more dangerous is that problems with sodium ion concentration changes in the ECF tend to come on much more gradually. The systems that are affected by potassium solute imbalance happen quite suddenly, right? And sometimes quite lethally, right? So give this some thought and we will talk about this issue together in class. All right, so this diagram from your book, just kind of puts everything together in terms of the sodium ion concentration in the extracellular fluid and how the body responds to changes in that solute's concentration in the ECF, right? So here we start at normal homeostasis. Sodium ion concentration is where it should be in the extracellular fluid, right? And then that concentration is changed and homeostasis is disturbed, right? So in this direction, we are decreasing the sodium ion concentration. And remember, usually the most common culprit of this is overhydration, right? We have too much water, right, in the extracellular fluid. Let's say we drank too much pure water too fast and we have diluted the sodium concentration in our extracellular fluid, right? Well, what's going to happen? Well, osmoreceptors that monitor sodium ion concentration in the hypothalamus detect this, and they are inhibited, so to speak. In other words, they do not stimulate the release of ADH from the posterior pituitary, right? As a result, we have a decreased thirst drive. As a result, we increase, right, urinary loss of water, in other words, water loss in the urine. We get less water reabsorption in the nephron, right? This loss of water concentrates the sodium ion concentration in the extracellular fluid, and homeostasis is restored, right? The other direction, we have an increase in sodium ion concentration, usually by dehydration, right? We either lose too much water or don't ingest enough, right? But we have too little water in the extracellular fluid fraction or compartment, and therefore our sodium ion concentration increases. In this case, the osmoreceptors in the hypothalamus are going to detect this, and they're going to stimulate the production and release of antidiuretic hormone from the posterior pituitary, which will increase our thirst drive, which will tend to have us bring in more water, more fluid, and that will also increase water reabsorption at the nephron and thus decrease loss of water in the urine, right? This additional water volume is going to dilute the ECF sodium concentration back to its homeostatically appropriate level, right? Resulting in a net increase in volume, all right? Because remember, one of the problems with dehydration is a loss of fluid volume in the ECF, including the intravascular portion of the ECF, right? In other words, volume of blood plasma drops. And when volume of blood plasma drops, then the pressure of blood plasma drops, and therefore the pressure that drives the flow of blood, and therefore the flow of blood drops, right? And that can be very dangerous. Now this diagram from your book is one I urge you to study very, very carefully, right? I like this because it, as I highlight over here, it integrates the response to changes in both fluid volume and solute concentration in our body fluids. And remember, it's mainly the extracellular fluid compartment that we're talking about. This is what is monitored by the compensatory mechanisms of our body. The intracellular fluid compartment is not directly monitored and therefore not directly regulated by these mechanisms, right? So if we start over here, as we did the previous slide, normal ECF volume, we're at homeostasis, and then something happens to disturb that volume, right? If we lose volume from our ECF, either because we've lost fluid, or it can be massive hemorrhage, it can be massive dehydration, or we lose both fluid and sodium, right? How could we lose sodium and fluid? Well, perspiration is one, right? Failure of the nephron, damage or disease, kidneys, we can lose fluid and sodium, right, in our urine. But whatever the mechanism, the volume of the ECF compartment has decreased. This results in decreased blood volume and therefore blood pressure, as we've stated, and therefore the volume of blood entering the afferent arteriole is going to be decreased. There's going to be decreased stretch of the cells of the juxtaglomerular apparatus, which results in their secretion of renin into the bloodstream, right? And that leads to eventually to the creation of angiotensin II and activation of angiotensin II, which travels to the adrenal glands, causing them to release aldosterone, right? Also, the hypothalamus is going to increase its secretion or synthesis and secretion from the pituitary gland of ADH. Both of these are going to travel to the nephron and cause increased sodium reabsorption in the collecting duct and distal tubule, and also increased water reabsorption in the collecting duct and distal tubule, both of which act to decrease loss of water in the urine, right? Remember, ADH also acts to increase our thirst drive, which increases our water intake, right? So both a loss of or a decrease in urinary water loss and therefore an increase in water reabsorption and an increased ingestion of water are going to bring the volume of the ECF back up to where it should be and homeostasis is restored, right? Now let's go the other direction. This is a situation in which the volume of the extracellular fluid has increased, either because we've gained too much fluid or we've gained too much sodium or both, right? Right? So in this case, we have increased volume in the intravascular compartment, and the right atrium of the heart, right, its walls are going to be stretched or going to be distended, right? And if you remember, we talked about ANP, right? Atrial natriuretic peptide. It's called atrial, right? Because it is released by cells in the wall of the right atrium of your heart, right? So when the wall of the right atrium of your heart is distended because of increased blood volume entering the right atrium, right? Atrial natriuretic peptide is released. And remember, the natriuretic peptides, their role is to inhibit aldosterone release, right? Inhibit aldosterone release. They decrease ADH release, and they decrease your thirst drive, right? So we end up getting less sodium reabsorbed in the collecting duct and distal tubule. We end up getting, less ADH, so fewer water channels are open for water to move from the collecting duct and distal tubule back into our blood vessels, right? So the end result of both of these is that we get less water reabsorption in the nephron and more water lost in the urine, right? Plus, the lack of ADH means our thirst drive is decreased, so we decrease our water ingestion, right? So we increase loss of water in the urine, we ingest less water, right? And because we have less aldosterone, we also do not increase our sodium reabsorption, and we lose more sodium in our urine. All of these things, right, all of these mechanisms integrate or combine to to cause a net loss of water in the urine. ECF volume decreases, and we end up reaching homeostasis once again at proper ECF fluid volume, right? So I urge you to study this diagram carefully, because if you understand the whys and the hows here, right? The mechanism, of each of these components, whether it's the natriuretic peptides, aldosterone, ADH, right? What they do and why they are activated, right? Depending upon an increase or decrease in ECF fluid volume. If you can fully understand, and better yet, explain the physiology of the slide to someone else, then I'd say you understand this concept of fluid and electrolyte balance very well, at least to the extent that I would expect you to. Now, the previous two slides really talked about sodium ion and the extracellular fluid, right? Let's talk a little bit more about potassium. They say we're going to talk in class about why maintaining potassium concentration, right? Potassium ion concentration at homeostatically appropriate levels is so critical. We're going to talk about that in class. But let's talk a little bit about potassium, right? And how its solute concentration is balanced, and where and how it can be altered, right? Or as we said, most of the potassium in the body is located in the intracellular fluid compartment, right? It's part of the cytosol. Now, when we're in the nephron, right, remember that in the distal tubule and collecting duct in the nephron, right? So here's the collecting duct, say, right? Remember we talked about aldosterone acting on sodium-potassium transporters in the collecting duct, right? If aldosterone comes along, is released by I'll just put ALD for aldosterone. Aldosterone influences this sodium transporter, causing it to reabsorb more sodium ion from the tubular fluid, right? Well, this sodium ion transporter is actually a counter transporter, in that every time a sodium ion is reabsorbed under the influence of aldosterone, a potassium ion is secreted into the tubular fluid, right? So every time we reabsorb a sodium ion from the tubular fluid and back basically into our bloodstream, we lose a potassium ion out to the urine, right? Via exchange. Okay? Now here we're really talking mostly about the potassium that is in the ECF, right? Most of the potassium is here in the ICF, right? So this potassium that's getting exchanged here in the collecting duct for sodium is really the potassium concentration in the ECF, right? So we can say down here that portion of the potassium ion concentration is governed by the function of the sodium potassium countertransporter in the DCT, in the collecting system of the nephron. Now, just like we can have hyponatremia and hypernatremia for sodium ions, so too we can have hypokalemia, right? Remember the K, right, stands as the symbol for potassium. Hypokalemia and hyperkalemia. In other words, the potassium ion solute concentration drops below homeostatically appropriate levels, which is right around 2 to 2.5 milliequivalents per liter, or rises above. Anytime it gets above 7 or 8, you're in trouble. And again, we're going to talk about what can happen and why this is so critical in class together. Now, under what conditions can the potassium ion concentration in the ECF get too high? Well, how about we have, renal failure. Renal failure such that, we, here we are in our nephron again, right? We have renal failure, and these transporters that reabsorb sodium ion and secrete potassium ion are non-functional, right? Non-functional. So that we cannot reabsorb sodium, and therefore, if we can't reabsorb sodium, we can't reabsorb water either in the collecting duct, right? And therefore, we're also going to get wasting of water in the urine because we can't reabsorb it. But also, right, if we're not reabsorbing sodium, we're also not secreting and excreting potassium. So potassium ion builds up, right, in the ECF, right, and becomes too high. Also, diuretic drugs, right? Diuretic drugs that increase the loss of water in the urine as a way of lowering blood pressure by lowering the intravascular volume of the ECF, right? They sometimes act by inhibiting these transporters, right? So certain diuretics called potassium-sparing diuretics actually work by inhibiting this sodium-potassium transporter. And if they inhibit that transporter, right, we do not get reabsorption of sodium ion back into the intravascular fluid, and therefore we don't get the reabsorption of water back in the intravascular fluid, and therefore the volume and pressure of the intravascular fluid, i.e. the blood pressure, drops, right? Drops because the blood volume decreases, right? But the problem is, if we inhibit the reabsorption of sodium, yes, we get a drop in blood volume, but we also are inhibiting the elimination of potassium. So here we have the situation again where potassium ion concentration is building, right? A third way, right, we can get hyperkalemia, or these are the most common, I guess I should say, is if we have a decline in the pH of the ECF. And remember, when pH drops, remember what pH means. pH refers to, right, pH is the negative log of the hydrogen ion concentration, right? In other words, the greater the concentration of hydrogen ions, the lower the pH, right? Because it's the concentration of hydrogen ions in the solution that's making it more acidic, right? So if the pH drops, what that means is the hydrogen ion concentration in the ECF has risen, right? Well, also in the distal tubule, mostly, and in the collecting duct to a certain extent, right? There are hydrogen ion transporters, right? Potassium and hydrogen ion transporters, right? That reabsorb potassium in exchange for hydrogen ion, right? So one of the ways the nephron compensates for a drop in pH, which is due to an increase in hydrogen ion concentration, is to increase excretion of hydrogen ion in the urine, right? But we do so at the expense of reabsorbing a potassium ion. So the more hydrogen ion we excrete to compensate for the drop in pH, the more potassium ion we're going to reabsorb. And if we do that to too great an extent, we can increase the concentration of potassium ion in the ECF beyond homeostatically appropriate levels, right?